I will store them at points. We have to transfer normals onto the centroid points. Let's display the normals and see how they look. That's it, now let's transfer to the centroid points. For that we can use an attribute transfer node. Plug the normals to the second input. Specify the normals from here. We can disable the primitives. Now let's check what we get. Here we go, the normals are transferred on centroid points. Okay, now let's dive inside and bring in these normals. Create an import point attribute. Connect the second geometry to it, which is centroid points. As point numbers we have to use the class attribute. We just need to specify the name of the attribute that we are going to import. Now let's drag this node closer to the rotation matrix. Connect the normals to the axis. Now let's tweak the angle and see what we get. Take a look, all pieces rotate around the normals. To avoid the overlapping, let's scale down a bit each piece. I think it's enough, now let's rotate them again. That's it, now it is clearly visible that they rotate around the normals. Okay, let's go ahead. Now I want to show you another way to perform similar matrix manipulations, during which you will learn new nodes and new techniques. Okay, let's drop down a new attribute VOP. Connect the torus to the first input. The centroid points to the second input. Let's give names to both attribute VOPs. This time I also would like to start with colors. First, let's bring in the class attribute. Now let's generate the random values based on the class attribute. I also want to fit the range of random values. Make the destination range from 0 to 2. Now I'm going to round the random values from 0 to 2 to get integer values. Let's export the result and see what we get in the attribute spreadsheet. I call it a test. Take a look, after rounding we got 3 integer values, 0, 1 and 2. Okay, let's go on. Now I want to generate 3 random colors based on these 3 integer values. Delete the bind expert node. Then create a random node. Connect to it the 3 integer numbers. Then select 3D color output and connect to the CD this color. Here we go, we got 3 random colors. Let's create an add constant just to add a seed. That's it, now we are able to change the colors. To change the total number of colors, we just need to change the destination range. Now let's put a 1, just to get 2 colors. Let's tweak again the seed and see how it looks. Now let's add a few more colors. Put a 4 for destination max. Here we go, now we have 5 colors. Let's again tweak the seed and see different variations of these colors. Nice, let's choose one of them and move on. That's it, I will stick to this one. Now organize this network a bit. Let's copy this one for further workflow. Then select all these nodes with regards to color setup and create a network box. Let's call it a color setup. Press C and choose a black color for the network box. Then minimize it just to free up a lot of workspace. Excellent, now let's get back to matrices. Let's create a make transform node. This operator builds a general 4x4 transform matrix. In this menu we can specify the order of translation, rotation and scale. Now let's multiply the position vector by this matrix. Look, now we can move, rotate and scale our geometry using only this single node. We even have a pivot that allows you to rotate and scale the geometry around it. Now let's import centroid points and use them as pivots. Connect to it the second geometry. As a point number we have to use the class attribute. Now let's connect the centroid points to the pivot. Let's check out what has changed. As you can see, each piece rotates about a pivot point, which in our case is the centroids. The same goes for scaling. The presence of a pivot simplifies the process since there is no longer a need to send all the pieces to the origin for further manipulation, then return them back. Okay, let's move on. Now I want to apply the transformation matrix only for specified pieces. I propose to group the centroid points, then use this group as a trigger in the attribute VOP. The group type must be points. I will call it an object because I'm going to group by object. Disable the base group, then enable keep in bounding regions. Choose a bounding object. Now we have to create some geometry and specify it as a bounding object. Let's choose a polygon. Increase the frequency. Then connect it to the second input. That's it, we have grouped all the points that are inside this sphere. Now let's move the sphere so that some part of these points remain outside. Okay, something like this. Here is our group inside 138 points. Now let's dive inside attribute VOP, then use this group as a trigger. To import a group, we can use the inGroup node. This operator returns 1 if the pointer primitive is in the group specified by the string. We must connect the geometry where the group is located. Let's enter the name of the group we are looking for. As a point number we have to use the class attribute. Now let's export the output of the inGroup node and see what we have. Call it test, then jump to the geometry spreadsheet. Look, we have 0 and 1. 0 means points are outside the group. 1 means the points are inside the group. Excellent, now we can use these values as a trigger. Let's create an if block. This block, which contains these two nodes, is a simple if construct. Look, if the condition is true, then all the manipulations that we are going to do inside this block will be performed. Now I want to demonstrate to you how it works. First let's give it a condition. Then create a constant. The constant type is going to be a color vector. Let's make it red. Then connect the color to the if block input. Now let's copy the geometry VOP output. Delete this connection. Then connect the color to it, already inside the block. Look, the pieces for which the condition is true became red. Now let's move the sphere, which we use to group the centroid points. Here we go, pieces that fall inside the sphere turn red. Now I propose, instead of changing the color, to make some manipulation with matrices. Okay, let's get rid of these two nodes, we don't need them anymore. Unplug this, then drag these nodes close to the if block. Excellent, now let's connect the position vector to the if block. Connect the same position vector to the multiply node, already inside the block. The product goes to the output. And finally, connect the block output to the P. We can arrange the nodes to avoid confusion. Now let's tweak the scale of the transformation matrix and see what it looks like. Here we go, only pieces for which the condition is true are scaled. Let's temporarily zero the scale. Then start moving the grouping sphere. That's it, the pieces that fall inside the sphere disappear because their scale becomes 0. Now I want to rotate them instead of scaling. Let's put a 1 for scale. For rotation, I'm going to use a noise. Let's drop down the turbulent noise. Connect the centroid positions to it. The output should be 3D noise, and the type will be original Perlin noise. Put a 360 for amplitude. Then connect the noise to the rotation. Okay, now let's move the grouping sphere and see how it looks. Definitely something is missing here. I suggest improving this setup and adding rotation fade closer to the surface of the grouping sphere. Okay, now we need a XYZ distance node, let's create it. This operator finds the distance to the closest primitive on the given geometry file. Connect the third geometry to it. Then jump to the object level and connect the grouping sphere to the third input. Now we must specify the positions from which we want to measure the distance relative to the sphere surface. Let's visualize the distance and see what it looks like. Look, closer to the surface of the grouping sphere the color becomes black because the distance tends to 0. Excellent, now I suggest using this distance attribute as a mask. Delete the visualize node, we no longer need it. Now we can multiply the noise by this distance attribute. Before multiplying, let's fit the distance. Let's adjust a source max. That's it, let's check what we got. Great, now the pieces rotate gradually, and we can control the sharpness of this gradient by editing the distance attribute. That's it, this concludes this lesson. The next lesson is also devoted to matrices, we will study other important nodes associated with them.